Welcome everyone. Today we are going to explore how to numerically solve second-order ordinary differential equations, which are fundamental in describing many physical phenomena. The primary challenge we will address is that common numerical solvers, like those in SciPy, are designed for first-order ODEs, or systems of first-order ODEs. Therefore, our main learning objective is to understand how to transform a single second-order ODE into an equivalent system of two first-order ODEs. This conversion is a crucial skill, as it unlocks the power of these solvers for a broader class of problems. We will begin by looking at familiar examples from physics that are modeled by second-order ODEs. For instance, we will consider the motion of an object in free fall under gravity, including the effect of air resistance, described by the equation. The second derivative of position y with respect to time t equals the acceleration due to gravity g, minus a drag term k over m times the first derivative of y with respect to t. We will also examine the classic simple pendulum, whose motion is governed by the equation. The second derivative of angle theta with respect to time t equals negative g over L times theta, where g is gravity and L is the pendulum length. This session will equip you with the foundational technique to tackle these types of equations numerically. Continuing our exploration of second-order ODEs, let us consider a more complex system, the damped pendulum subjected to an external driving force. Its equation of motion is given by the second derivative of the angle theta with respect to time t equals negative omega squared times theta, minus a damping term 2 zeg omega times the first derivative of theta with respect to time, plus a driving term f hat times sine of omega sub dt. Here, omega squared is g over L, zeg o represents the damping ratio which depends on the drag coefficient k and mass m, and f hat incorporates the external driving force F sub d. This single equation captures rich physical behaviors like critically damped, underdamped, or overdamped oscillations depending on the damping ratio δ, and resonance phenomena when the driving frequency omega sub d is close to the natural frequency omega. Another significant second-order ODE in physics is the one-dimensional time-independent Schrödinger equation, which describes quantum mechanical systems. It states that negative h bar squared over 2 meters times the second derivative of the wave function psi with respect to position x equals the quantity E minus v's of x, all multiplied by psi of x, where E is energy and v of x is the potential energy. A key point for numerically solving any such second-order ODE is the necessity of providing two initial conditions, typically the value of the function and its first derivative at some initial point. Now, let us formalize the general structure of a second-order ordinary differential equation that we aim to solve. It can typically be written as the second derivative of y with respect to x equals some function f, which may depend on y, x, and possibly the first derivative of y. For example, we might encounter an equation like the second derivative of y with respect to x equals negative x squared times y, with given initial conditions for y and its first derivative at some starting point x0. The core technique for solving such equations, using tools like SciPy's ODE function, involves converting this single second-order ODE into a system of two first-order ODEs. We achieve this by introducing a new variable, let us call it y dot, defined as the first derivative of y with respect to x. With this substitution, our original second-order equation transforms into two coupled first-order equations. First, the derivative of y with respect to x is simply y dot, by definition, and second, the derivative of y dot with respect to x is equal to our original function, f of y x. We then need to create a Python function, often called a model function, that takes the current state, which is a pair of values y and y dot, and the independent variable x, and returns the derivatives, which are y dot and f of y x, respectively. This model function is then passed to the ODE solver, along with initial conditions and the range of x values, to obtain the numerical solutions for both y and y dot. Let us now apply this method to a concrete example. We will numerically solve the second-order differential equation. The second derivative of y with respect to x equals negative x squared times y. The problem specifies initial conditions at x0 equals negative 2, where y is 1, and its first derivative, y dot, is 0. We are interested in the solution over the interval of x from negative 2 to 5. The provided code block demonstrates exactly how to implement this. First, we import the necessary libraries: NumPy for numerical operations, ODE from SciPy for solving the ODEs, and matplotlib for plotting. Then, we define our model function. This function takes a two-element list depvars, representing y and y dot, and the independent variable invar representing x. Inside the function, it unpacks y and y dot, then calculates the right-hand side of the second differential equation, which is negative x squared times y. It returns y dot, and this calculated right-hand side, effectively providing the derivatives for our system of two first-order equations. Following the model definition, the code sets up the initial values for x, y, and y dot, creates an array of x values for which we want the solution, and bundles the initial y and y dot into a nitcond. The ODE function is then called with our model, initial conditions, and x array. The output from ODE contains the solutions for y and y dot, which are then extracted and plotted against x, allowing us to visualize the behavior of the function y of x and its derivative y dot of x. Let us reinforce our understanding by applying this technique to another classic physics problem: the simple harmonic pendulum. The equation of motion for small oscillations is given by the second derivative of theta with respect to time t equals negative omega squared times theta, where omega is the angular frequency related to gravity g, and pendulum length L by omega equals the square root of G over L. We know the analytical solution involves sinusoidal functions, but our goal here is to solve it numerically. To do this, we first convert the second-order ODE into a system of two first-order ODEs. We define theta dot as the first derivative of theta with respect to time. Then, our system becomes: the derivative of theta with respect to time is theta dot, and the derivative of theta dot with respect to time is negative omega squared times theta. The code implements this by first setting up physical parameters like g, L, and calculating omega and the period t. It then defines the model function. This function takes depvars, theta and theta dot, the independent variable in var, time t, and an additional params argument which passes the value of omega. Inside, it calculates the right-hand side, negative omega squared times theta, and returns theta dot and this value. Initial conditions for theta, a small angle of 4 degrees, and theta dot, 0 meaning released from rest, are set. An array of time points tar is created, spanning several periods of oscillation. Finally, ODE is called with the model, initial conditions, time array, and the args parameter to pass omegas. The solutions for theta and theta dot are extracted from the output and plotted, visualizing the pendulum's angular position and angular velocity over time. In this lesson, we have focused on a fundamental technique for numerically solving second-order ordinary differential equations. The key takeaway is the method of transforming a single second-order ODE into an equivalent system of two first-order ODEs. This is achieved by introducing a new variable that represents the first derivative of our original dependent variable. By doing so, we can define a model function that describes the rates of change for both the original variable and its first derivative. This model function, along with the necessary initial conditions, can then be used with standard numerical solvers, like SciPy's ODE function. We saw this approach in action through examples such as a general second-order equation and the simple harmonic pendulum, demonstrating how this conversion allows us to effectively simulate and understand the behavior of various physical systems. This systematic process of reduction to a first-order system is a powerful and widely applicable tool in computational physics and engineering.